So let's talk about physiology of the heart, or how the heart works. So we talked about autorhythmicity of the heart, that the heart can create its own action potentials. So how does it do that? Well, in this diagram we see in yellow pacemaker cells. Pacemaker cells are not neurons or nervous tissue. They kind of look like that in this drawing, but they're not. They're simply modified cardiomyocytes. So typical cardiomyocytes are specialized for muscle contraction so that the heart can beat. But the pacemaker cells are specialized for generating action potentials and for passing along action potentials. So there's different names for different regions of these pacemaker cells, different clusters. So the first cluster of pacemaker cells is called the Xenoatrial Node. Xenoatrial Node. And we call that the SA node for short. Then we have the Atrioventricular Node. Or AV node for short. Then we have this is called, there's two names for this. You can call it the bundle of His, or the atrioventricular bundle. I personally like atrioventricular because I like intuitive names, and these are between the atria and the ventricles. So you have the node between the atria and the ventricles, and you have the bundle between the atria and the ventricles. Now the bundle of His, or the atrioventricular bundle, branches, and you then have the left and right bundle branches. That's easy. These scoop down to the apex of the heart and then back up the sides of the ventricles. And these finer branches have two names as well. You can call them Purkinje fibers, or you can call them subendocardial conducting network. The action potential always starts in the Xenoatrial node. So the Xenoatrial node in a healthy heart sets the pace. The pacemaker of the heart. So it generates action potentials in a rhythmic fashion at around 75 beats per minute, give or take. And now our nervous system can modify that heart rate, so it's not always exactly the same. Like when you're exercising or you're scared or you're relaxing, your heart rate will be modified by your nervous system. But the base rate is set by the Xenoatrial node at 75 beats per minute. And when the Xenoatrial node is setting the rhythm of the heart as it's supposed to do, we call it a sinus rhythm, and that's normal. A normal sinus rhythm. Right. So the Xenoatrial node will generate action potentials, pass them to the atrioventricular node, which then passes it down the atrioventricular bundle, down to the left and right bundle branches, and to the Purkinje fibers. Now, if the Xenoatrial node for some reason is damaged and it no longer works, your atrioventricular node will take over as pacemaker of the heart. The thing is it's slower. It's around 40 to 60 beats per minute. So you would just have a slower heart rate if that happened. And if for some reason both the Xenoatrial node and the atrioventricular node go out, there are other nodes, other clusters of pacemaker cells that can take over, but they're so slow, they're like 20 beats per minute or less. It's not fast enough to stay alive. Your heart needs to beat faster than that, so you would need a pacemaker to survive that. So the reason the Xenoatrial node sets the rhythm is just because its rhythm is faster than all the other pacemaker cells. So other pacemaker cells do generate their own rhythms, but they're slower. So because the Xenoatrial node is the fastest, it's always firing first. And when it fires an action potential, that action potential is shared. The action potential will pass from the Xenoatrial node to all the other pacemaker cells in the heart through the gap junctions, causing each of them to fire in turn in this wave-like fashion from the top of the heart to the bottom of the heart. It doesn't only pass the action potential to the other pacemaker cells. It also passes the action potential to all the neighboring heart cells, heart muscle cells. And that's indicated by those arrows that were already there. So the action potential spreads through the entire atria from top to bottom. And that causes, and when a muscle cell, including a cardiac muscle cell, receives an action potential, it stimulates the muscle cell to contract, as you might remember when you were studying skeletal muscle. So the contraction follows the pattern of the spread of the action potential. So action potential moves in this wave-like fashion from top to bottom of the atria. The contraction starts at the top of the atria and then moves down to the bottom of the atria, and that causes the blood to squeeze downwards because of that contraction. Now, there's this division here called the Atrioventricular Septum. Septum just means divider. Atrioventricular means the dividers between the atria and the ventricles. This is an insulator. It's just made of that fibrous skeleton we talked about. It's made of just connective tissue. But because it's an insulator, that electrochemical charge of the action potentials cannot pass through the atrioventricular septum. It's stopped in the atria, except right here. So the AV node is the gateway for action potentials to pass to ventricles. And then all that action potential has to be funneled down the atrioventricular bundle. So the AV bundle, or the bundle of His, is a bottleneck. It's an action potential bottleneck. So action potentials, AP for action potentials. So this causes the action potentials to slow down. They spread almost instantaneously through the atria, but then because of this bottleneck, they seriously slow down before they can make it to the ventricles. And that's important too, because you don't want the atria and the ventricles contracting at the same time. You want a more coordinated movement, atria then ventricles, atria then ventricles. This makes sure the blood goes down and out, down and out. So the bottleneck causes a slowdown, the atria start to relax, and then the ventricles contract. And the contraction starts in the apex and moves upwards. This central divider where the bundle branches are, it does contract, but it's a mid-wall, so the middle wall gets skinnier when it contracts. But you really get the volume, the chambers contract when the outside, when the outside of this ventricular wall contracts. So the contraction really starts at the apex and travels up the ventricles so that the blood can move out these large arteries that leave the heart. So how do these pacemaker cells create their own action potentials? They have some very interesting ion channels. So remember, an action potential is just a change in the membrane potential. So the resting membrane potential is very negative. The inside of the cell membrane is very negative compared to the outside of the cell membrane. So when you bring a lot of positively charged ions in, that change in membrane potential is what we see when we look at these action potential graphs. So let me label this action potential of pacemaker cells in the heart. So let's start here. We're going to say this low point where it's the most polarized, where the inside of the cell is the most negative relative to the outside of the cell. That's our starting point. Step 1. These pacemaker cells are really interesting in that they have no resting membrane potential. The membrane potential is never still. It's never flatlined because it has these leaky sodium channels. So you have a slow movement of sodium into the pacemaker cell. So the cell gets as negative as it can get, but these sodium channels are just always open a little bit. And sodium's just leaking slowly into the cell. And that's bringing the resting, it's not a resting potential, right, because it's moving. That's bringing the membrane potential slowly up until it reaches threshold. Once threshold is reached, you get this action potential because voltage gated calcium channels open. Sorry, that was an error. Voltage gated channels are channels through the cell membrane that open or shut in response to membrane potential or in response to the electrochemical charge or electrochemical gradient across the cell membrane. So the sodium channels allow sodium to leak into the cell, making the inside of the cell more positively charged. And once the inside of the cell is positively charged enough, it triggers the calcium channels to open, and these open and allow a flood of calcium in, so you get the action potential. Here's the action potential right there. So this is a spike we call this depolarization. At the top here, this will be number 3, calcium channels close. And I should mention, let me go back to number 2. Calcium comes in. Calcium in. So once you reach a certain charge, once the action potential is high enough, the calcium channels will be stimulated to close and the potassium channels will open. And potassium goes out. Now, all of these ions are positively charged. In the case of sodium and calcium, the positive charge is coming into the cell. In the case of potassium, it's going out of the cell. So we're losing positive charge. This inside of the cell is becoming more negative is what that means, because we're getting rid of positive charges. So that brings us back down. We call this repolarization. Repolarization. Once we're down here, we're back at the beginning. The potassium channels close, but the sodium channels are always open. They're just leaking the whole time. So we start the cycle over again. The inside of the cell becomes slowly more positive because of the leaky sodium channels until the threshold is reached. Then you get the spike because of the influx of positively charged calcium. Calcium channels close and potassium channels open. Potassium moves out of the cell, making the cell more negative and repolarizing. And then we start over again. So the rhythm of this is set by how leaky the sodium channels are. The leakier they are, the faster action potentials fire. And they're leakiest in the Xenoatrial Node. So that's why the Xenoatrial Node always fires before the other pacemaker cells. Now, this action potential, these ions, these positively charged ions, are being shared through the gap junctions with neighboring pacemaker cells. And so the action potential gets spread through the entire heart. the action potential spreading from the Xenoatrial node will cause the Atrioventricular node to reach threshold and to beat at approximately the same time. Now, these action potentials don't just spread to other pacemaker cells. It also spreads to the other cardiomyocytes, the muscle cells designed to contract when they are innervated by an action potential. I don't want to say innervated because, again, these are not nerves, but when they're stimulated by an action potential. But the cardiomyocytes are different. Cardiomyocytes are not autorhythmic. They will not create an action potential on their own. They will not contract unless stimulated by an action potential from a neighboring cell. So here's what a cardiomyocyte looks like. These, so action potential, cardiomyocytes. The starting point is here, we'll say, ions from neighboring heart cells. Ions from neighboring heart cells, neighbor heart cells, bring cell to threshold. So maybe the neighboring cell is a pacemaker cell, maybe it's another cardiomyocyte. So you get this influx of ions from the neighboring cell, and that causes fast sodium channels to open, and you get this really fast spike for the action potential. So fast sodium channels open. And again, the sodium comes into the cell. So the difference here is that the sodium channels in the pacemaker cells were leaky. It was a slow rise in membrane potential. Here, a little bit of stimuli from a neighboring cell is going to create a dramatic spike because of fast sodium channels, allowing a rapid rush of sodium, positively charged sodium, into the cell. All right, now this part is a little complicated. There's a couple things that are going on at the same time. So first thing that happens is that K+ channels open, and K+ moves out. That causes a decline here. So ignore the original numbers. I'm making my own numbers. So the potassium, the positive charged potassium, is leaving. Positive charge is leaving, the inside of the cell is becoming more negative, so you're starting to get some repolarization here. But another thing is happening at the same time that makes this repolarization really slow. You get this kind of plateau here. So let's say here we have number 3, calcium channels open, and calcium comes in. Now the calcium channels, these are in the sarcoplasmic reticulum. You have those in skeletal muscle also. The sarcoplasmic reticulum is just an organelle that stores calcium. So once you reach a certain membrane potential, potassium channels open, letting potassium out. Calcium channels open, allowing calcium in. And so so the calcium raises the membrane potential, potassium lowers it. The reason you still have this overall downward trend is because more positive charge is leaving than coming in. So you have more positive charge leaving the cell than positive charge entering the cell. But because these two forces of positive out, positive in are battling each other, you get this long plateau. So cardiomyocytes are unique in that they have this very long, stretched out action potential. Then eventually, the calcium channels will close. So we'll say it happens like somewhere around here. Calcium channels close. But the potassium channels stay open until all the way down here. So once the calcium channels close, potassium's going out. You get a faster downward trend for a faster repolarization. And then finally, when you get all the way back to the original resting membrane potential, that's when the potassium channels close. Why do calcium channels open? Well, you might remember from skeletal muscle studies that the calcium has to be there for the muscles to contract. And remember, actin and myosin filaments, they have to ratchet past each other to cause that muscle to shorten and contract. The binding sites between the actin and myosin are blocked. The calcium unlocks them. So the calcium in, and then also another little calcium unlocks binding between muscle fibers, allowing contraction. So as long as calcium is in the cell, the heart cell can contract. And because there's this like long plateau, you have a very long contraction in heart cells. All right, so to recap, the pacemaker cells make the heart's rhythm by creating their own action potentials. The threshold for action potential is reached at a steady pace because of these leaky sodium channels that slowly reach threshold over and over and over again at a steady pace. And that allows the ions to float into the cell, though there's no resting membrane potential in the pacemaker cells. Threshold causes ion channels to open and a rapid depolarization of the pacemaker cells as positive ions flood the pacemaker cells. These ions also spread to neighboring pacemaker cells and neighboring cardiomyocytes through gap junctions in the intercalated discs. And that brings these neighboring cells to threshold, creating action potentials in a wave-like fashion through the heart. Action potentials cause cardiomyocytes to contract, so contraction moves through the heart also in a wave-like fashion. The Atrioventricular Septum is an insulator, so action potentials cannot pass from the atria to the ventricles except through the atrioventricular bundle, or the bundle of His. This creates a bottleneck and a serious slowdown of the action potential. This accounts for the delay between atrial contraction and ventricular contraction. So blood is squeezed from the atria into the ventricles first, and then out of the ventricles into the pulmonary or systemic circuit of the body. So as atria begin to relax, ventricles contract. Depolarization is followed by contraction. Repolarization is followed by relaxation of the heart muscle. This graph is an EKG, which stands for electrocardiogram. In an electrocardiogram, electrodes are placed on various parts of the body to measure the movement of an electrical signal. In this case, they're measuring the movement of the electrical signal through the heart. They are not measuring whether the signal is positive or negative. They're just measuring the direction of flow. So whether a positive charge is moving towards the electrode or a negative charge is moving towards a particular electrode, it's going to look the same. The EKG will only look different if the leads are misplaced, because if you change the position of the leads, it's going to change the direction of electrical movement relative to the leads. So these are not telling you, this is a problem I get all the time, people think that this is more positive, like when we're looking at the action potentials, up is positive and down is negative. No, that's not the case. This is just towards a lead or away from a lead. So towards or away. So it's just the direction of the movement of the signal. So this is a normal EKG, and there are these different waves that are given these different letters. And we're going to focus on the P wave, the Qrs complex, and the T wave. So the P wave is showing you the wave of depolarization as it moves through the atria. Of depolarization through atria. The Qrs complex shows you two things simultaneously, because there's two things happening at once in the heart at this time. You have a wave of repolarization through atria and wave of depolarization through ventricles. And then we have the T wave. The T wave shows you the wave of repolarization as it moves through the ventricles. Wave of repolarization. So remember that depolarization is when you have a spike in positive charge, and so depolarization is a spike in positive charge, repolarization is a spike, or is a drop back to a negative charge. And in every case, you see an upward spike, because like I said, the EKG is not showing you positive versus negative. It's just showing you whether a signal, be it positive or be it negative, whether it's moving towards a particular electrode or away from it. So it's a towards away thing, not a positive or negative thing. Whether it's negative moving towards or positive moving towards, it's going to look the same. Now, there's a slight delay between when the action potential passes through the myocardium and when it contracts. So you have an action potential first and then contraction. The EKGs here, they only show action potential movement. They don't show contraction. You're going to have to infer when the contraction happens. So this image shows depolarization in yellow and repolarization in red. So first you have the P wave, which represents the wave of depolarization spreading through the atria up here in image 1. Here, in what's known as the PR segment, that's when you have atrial contraction. So atrial contraction. All right. Then you have the Qrs complex, which has two things happening at once. You can see the wave of repolarization moving through the atria at the very same time that the wave of depolarization is starting to move through the ventricles. So that's the Qrs complex in number 3. In number 4, you have this ST segment. So this is PR. Oops. PR segment, ST segment over here. This ST segment, this is when ventricular depolarization is complete. That's when you start to get contraction. Ventricle contraction. Number 5, ventricles are repolarizing. That's when the ventricles begin to relax. And actually, let me put that in 2. So whenever you see repolarization happening, that's when the muscles are beginning to relax. So ventricles begin to relax. Because repolarization, when it comes to the muscle cells, the ones that contract, not the pacemaker cells, when they're repolarizing, the calcium is being taken away. And that's going to stop the myosin and actin filaments from moving past each other. So the heart will have to relax at that point. So when you see ventricle repolarization, that's ventricles relaxing. When you see atrial repolarization, like you see in number 3 over here, the atria are beginning to relax. All right. So now you have an overlay of action potential movement and contraction. Now, an arrhythmia is any deviation from the normal sinus rhythm. Remember, sinus rhythm is created by the Xenoatrial Node. So here you see ventricular fibrillation. This is characterized by a chaotic action potential movement in the ventricles because of a lack of oxygen reaching all the cells. And what happens is basically not all cardiac cells are working properly. So the action potential travels chaotically through the ventricles. The ventricles can't contract properly because the action potentials are just moving like crazy throughout them. So the action potentials keep returning to the same cells over and over and over again. It's not moving smoothly through and out, through and out. To surgeons who are looking at a heart that's doing this, the heart seems to squirm and writhe about unnaturally, kind of like a bag of worms. So so this is ventricular fibrillation. Defibrillation is when you give a person who's experiencing ventricular fibrillation a strong electric shock that electrifies all the cardiac tissue at once, in hopes that once all the cardiac tissue is in the refractory period at the same time, the Xenoatrial Node will take over properly again and the sinus rhythm will resume. That doesn't fix the underlying problem, which is a blockage, an artery blockage, and a lack of oxygenation. So that problem's still there, but it's sort of like a resetting of the heart. It's an electric shock to all cardiac muscle at once. Then all go into refractory period at once. SA takes over normally again. So it's a reset button. The defibrillator is a reset button. So here's just another couple kinds of arrhythmias. You have atrial fibrillation at the top. Atrial fibrillation is where the atria are not passing the action potential correctly. So there's chaotic stimulation of the atria. But once the signal gets to the atrioventricular node, because there's that funnel, it passes all right to the ventricles. It might pass at an unusual rate because the atria are contracting at an unusual rate, but at least you get contraction of the ventricles. So you can recognize this because you can see the Qrs complex, which it represents the ventricles depolarizing. And sometimes you might even see a T wave, but you don't see any P waves. So you don't see the atrial component here, because you see chaos so chaos where P wave should be, where atrial depolarization should be. So heart blocks are where the atrioventricular node is not working properly, and so signals are not passing properly from the atria to the ventricles. So here, there's like you can see in the one on the left, there's a normal sinus rhythm. So you have P wave, QRS, T wave, P wave, QRS, T wave. This one on the right, you have the starting P wave, but the QRS and T are missing. So the signal was dropped for some reason between the atria and the ventricles. So that's a heart block, is where the signal is blocked from the top chambers, between the top chambers and the bottom. And so you can see that again down here. So again, you have the P wave representing atrial depolarization, but for some reason that action potential is not passed to the ventricles. And then here you have a whole bunch of P waves on the bottom right, down here. Whole bunch of P waves with almost no QRS complexes. So that's really bad, because this means that the heart isn't pumping blood to the body because the ventricles aren't contracting.